Welcome everyone. Today, we'll discuss the dangers posed by CO₂ and H₂S corrosion in the oil and gas industry. These gases not only damage infrastructure but also create serious safety and economic challenges. CO₂ and H₂S are critical threats in oil and gas operations. Understanding why they are so dangerous is the first step toward effective prevention. Carbon dioxide or CO₂ and hydrogen sulfide or H₂S are two of the most aggressive corrosive agents encountered in oil and gas environments. Their presence in production streams creates highly acidic conditions that attack steel infrastructure, leading to severe degradation. CO₂ dissolves in water to form carbonic acid, while H₂S forms hydrosulfuric acid, both of which significantly lower pH and accelerate corrosion. These gases are not only destructive to metal integrity but also pose serious health hazards, making them a dual threat to operational safety and reliability. Understanding their mechanisms and combined effects is essential for engineers and operators to prevent catastrophic failures and ensure safe operations. Next, let's look at how each gas contributes to corrosion and why their combined effect is so severe: CO₂ corrosion mechanisms, H₂S corrosion mechanisms. CO₂ corrosion occurs when carbon dioxide dissolves in water, forming carbonic acid or H2CO3. This acid reacts with steel surfaces, leading to uniform corrosion and the formation of iron carbonate or FeCO3 scales. While these scales can offer some protection, they are often unstable under fluctuating conditions. Factors such as flow velocity, temperature, and pressure influence the rate of CO₂ corrosion. In oil and gas pipelines, CO₂ corrosion is a primary cause of wall thinning, which compromises structural integrity and increases the risk of leaks or ruptures. Hydrogen sulfide introduces additional complexity to corrosion processes. When dissolved in water, H₂S forms hydrosulfuric acid, which aggressively attacks steel surfaces. Unlike CO₂, H₂S often leads to localized corrosion such as pitting, which is more dangerous because it can penetrate deeply into metal without significant overall material loss. H₂S also promotes the formation of iron sulfide or FeS films, which may provide temporary protection but are easily disrupted under dynamic conditions. The presence of H₂S significantly increases the risk of sudden failures in critical components. When CO₂ and H₂S coexist, corrosion becomes much worse. Let's explore why. Combined impact of CO₂ and H₂S, film interference and pitting. When CO₂ and H₂S coexist, their combined effect on corrosion is far more severe than either gas alone. CO₂ tends to create iron carbonate scales, while H₂S interferes by forming iron sulfide, destabilizing protective layers and exposing fresh metal surfaces. This interaction accelerates corrosion rates and promotes localized attack. Environmental factors such as temperature and gas concentration further influence this synergy. At lower temperatures, H₂S increases corrosion severity, while at very high temperatures, it may form more stable films that slightly mitigate damage. Understanding these interactions is crucial for designing effective mitigation strategies. Protective films like iron carbonate and iron sulfide play a key role in corrosion control, but their stability is highly sensitive to environmental changes. H₂S can disrupt iron carbonate layers formed under CO₂ corrosion, leading to localized pitting. Pitting is particularly dangerous because it is difficult to detect and can cause sudden equipment failure. The interplay between these films creates unpredictable corrosion patterns, making monitoring and preventive measures essential for maintaining pipeline integrity. Toxicity and exposure hazards. Beyond corrosion, H₂S is extremely toxic. Let's review its health hazards. Hydrogen sulfide is extremely toxic, with effects comparable to cyanide. At concentrations of hundreds of parts per million, ppm, H₂S can cause respiratory paralysis and death within minutes. Even at lower levels, exposure leads to irritation of the eyes and respiratory tract, headaches, dizziness, and long-term neurological damage. Its characteristic rotten egg smell is detectable only at low concentrations. At higher levels, olfactory fatigue sets in, making detection impossible without instruments. Strict safety protocols, including gas detection systems and personal protective equipment, are mandatory in environments where H2S is present. Cost and infrastructure damage. Corrosion doesn't just affect safety, it has major economic consequences. Corrosion caused by CO2 and H2S drastically reduces the lifespan of pipelines, pressure vessels, and other critical infrastructure in the oil and gas industry. Frequent replacements, unplanned shutdowns, and maintenance activities lead to massive economic losses. Beyond direct costs, corrosion-related failures can result in environmental contamination, regulatory penalties, and reputational damage. The operational impact includes reduced productivity, increased downtime, and heightened safety risks, all of which underscore the importance of proactive corrosion management. Finally, let's discuss how to prevent and manage these risks, preventive measures and monitoring, summary, and key takeaways. Effective mitigation strategies include selecting corrosion-resistant materials, applying protective coatings, and using chemical inhibitors to reduce corrosive activity. Continuous monitoring of gas concentrations, pH levels, and corrosion rates is essential for early detection and intervention. Advanced techniques such as smart sensors and predictive analytics can help anticipate corrosion trends and optimize maintenance schedules. Ultimately, a comprehensive approach combining material science, operational controls, and safety measures is necessary to manage the dual threat posed by CO2 and H2S. CO2 and H2S represent a significant challenge for the oil and gas industry due to their corrosive nature and health hazards. Their synergistic effects accelerate metal degradation, while H2S toxicity poses severe risks to personnel. The economic consequences of corrosion are substantial, making prevention and monitoring critical priorities. By understanding the mechanisms, environmental influences, and mitigation strategies, operators can enhance safety, reliability, and cost efficiency in managing these aggressive environments.